Welcome to the Explainer. Okay, let's just dive right into this, because today we're taking on what might literally be the ultimate astronomical investigation of our time, finding a true Earth twin. You know, we look up at the night sky, and it's so easy to just assume that somewhere out there, floating in the infinite blackness, there's another blue marble just waiting for us to find it. But the deeper we dig into the actual data from our space telescopes, the more we're realizing that an Earth 2.0 requires an incredibly specific, wildly rare set of circumstances.
So it really begs the question, the central mystery of modern astrophysics really. If there are billions of planets in our galaxy alone, why is it so incredibly hard to find one we could actually live on? For a long time, everybody was hyper-focused on just the habitable zone. You know, finding a planet orbiting its star at just the right distance so liquid water doesn't boil off or freeze. Not too hot, not too cold. But as the source material for this explainer reveals, finding that perfect orbit, that's nowhere near enough. To actually understand planetary habitability, we have to start by interrogating the stars themselves.
And here is the first major plot twist in our investigation. When you or I think of a star, we naturally picture our own sun, right? A G-class star. But sun-like stars are actually super rare. They make up a measly 6% of the Milky Way's population. The galaxy is completely dominated by red dwarfs, also called M stars, which account for a massive 73% of all the stars out there. So just by the simple law of averages, the vast majority of rocky planets we find are going to be orbiting these much smaller, much cooler red dwarfs.
Now, let's contrast these prime suspects for a second. You'd probably think a red dwarf's incredible lifespan, we're talking over 100 billion years, would be absolutely perfect for the slow, steady evolution of life. But there's a huge catch. Red dwarfs spew out harmful radiation that could be 80 to 500 times more intense than what we get from our sun. I mean, that is absolutely planet-frying. It basically completely eliminates M stars as a good candidate for advanced life. Instead, the data points us straight toward the K dwarfs, the orange stars. They live for 15 to 45 billion years, but their radiation is way milder, only 5 to 25 times more intense. When you balance out all those variables, K dwarfs emerge as the true Goldilocks stars.
Let's open up a specific suspect profile, Kepler 186f.
We're going to zoom in on a very famous suspect here, sitting quietly about 500 light-years away from us in the constellation Cygnus. On paper, its credentials are breathtaking. Kepler 186f was literally the very first validated Earth-sized planet ever found orbiting in a habitable zone. It's less than 10% larger than Earth, making it extremely likely to be a rocky world, and it completes a full orbit every 130 days. But here is the crucial detail. Because its host star is cooler, Kepler 186f only gets about 1/3 of the solar energy that Earth does. So if you were standing on its surface at high noon, looking up, the star would only look about as bright as our sun does an hour before sunset.
Which sounds kind of peaceful, right? A permanent golden hour? But the really close proximity these planets need to have to their smaller stars just to stay warm introduces the second huge twist in our cosmic detective story. What happens when a planet orbits that close to its host star? Well, we run into a mind-bending physics phenomenon.
And that phenomenon is called tidal locking. Just like our moon is tidally locked to Earth, which is why we only ever see one side of it, a planet can get tidally locked to its star. The researchers outlined two main scenarios for these rocky planets. First is a perfect one-to-one resonance, where the planet's day matches its year exactly. One side is permanently baked in daylight, the other frozen in eternal, pitch-black night. The second scenario is a 3-to-2 imperfect resonance, where the planet manages 3 full rotations for every 2 orbits, giving it an incredibly, agonizingly slow spin.
To understand why this happens, think of it like this. A planet isn't just a perfect, tiny point in space. It's a massive, extended body. So the star's gravity actually pulls slightly harder on the near side of the planet than on the far side. This physically stretches the planet out, creating what's called a tidal bulge. Now, if the planet is spinning faster than it orbits, that bulge is constantly getting yanked back by the star's gravity. Over millions, even billions of years, that gravity acts like a relentless set of brakes, slowing the planet's rotation down until it's completely trapped in one of those resonances.
So how do we know what that does to a world? We simulate it. Enter the V-Planet test.
To figure out if these exoplanets could actually harbor life, researchers fired up a highly advanced simulator called V-Planet. And to make sure it was a truly fair test, they established an Earth-like hypothesis as their baseline. Basically, they wanted to give these planets the absolute best possible shot at having liquid water. They assumed rocky mass and radius based on our best data. They gave each planet a nice Earth-like atmosphere with our exact greenhouse gases, tossed in a 2,500-meter deep global water ocean, and assumed absolutely no massive moons were around to complicate the gravitational math.
The data that came out of this simulation was fascinating. The time it actually takes for a planet to get trapped into tidal locking depends heavily on two things: the planet's initial spin and its orbital eccentricity, meaning how oval-shaped its orbit is. If a planet has an initial eccentricity lower than 0.23, it is destined for a perfect 1-to-1 resonance. If it's higher than that, it's heading straight for a 3-to-2 resonance. And basically, the faster the initial spin, the longer it can fight off getting trapped.
Well, the V-Planet simulator handed down its verdicts, and honestly, they're pretty stark. When researchers compared the time needed to get trapped against the actual age of the host stars, they discovered a really divided universe. Planets like Kepler 1126c and 1544b, they survive as fast rotators, meaning they haven't been caught in the trap yet. They managed to maintain habitable climates, though I should mention 1126c is sitting at a very warm 84 degrees Celsius. But then, you look at Kepler 440b. The simulation confirms it's fully tidally trapped, and the resulting climate model shows it to be completely, 100% frozen over.
And hey, remember our prime suspect from earlier, Kepler 186f? The one that made all those huge global headlines? Well, the data actually delivers some pretty heartbreaking news. Because we don't have hard constraints on its eccentricity yet, we don't know its exact spin. But as it turns out, it doesn't even matter. The simulations show that even with a perfect Earth-like atmosphere, Kepler 186f is just way too cold to sustain liquid water anywhere on its surface, no matter if it's a fast rotator or if it's tidally tracked. Without a significantly thicker blanket of an atmosphere to really pump up the greenhouse effect, it is, sadly, nothing more than a frozen rock.
But that leads us directly to the ultimate mystery: Kepler 442b. With 186f basically out of the running, all the data suddenly points us to what is easily the most fascinating suspect of all. Because we don't know its exact orbital eccentricity, Kepler 442b essentially has three vastly different possible fates. If it's a fast rotator, it's a cool but perfectly habitable world at about 8 degrees Celsius. If it's locked in a 1-to-1 resonance, it's still surprisingly habitable right at the substellar point, that bullseye spot directly facing the star. But look at that third outcome. If it's locked in a 3-to-2 imperfect resonance, spinning very slowly, it becomes irreversibly frozen. And incredibly, the data shows its global temperature would actually drop colder than the permanently dark side of a 1-to-1 locked planet. No way, right?
So the absolutely crucial thing to wrap our heads around here is why an imperfect slow spin is actually somehow worse for a planet than being completely locked with half the world in permanent darkness. It all comes down to ice and reflection. See, in a slow spin, a massively thick ice mantle forms during the very long night. When that icy surface finally slowly rotates back into the sunlight, that bright white ice has a huge albedo, meaning it acts like a giant mirror, reflecting almost all the star's warming energy straight back into space.
The melting process is just way too slow. Before the daylight can even begin to defrost the oceans, the planet's slow rotation just carries it right back into the freezing night. And while that's happening, fresh ice is already forming on the other side. It's a runaway deep freeze that literally outpaces the planetary sunrise. This creates a wildly counterintuitive reality. A slow rotation creates such a high global reflection of energy that it starves the planet of heat entirely. It actually makes it colder overall than a planet with a fixed permanent dark side, because at least that locked planet is constantly absorbing heat on its sun-facing half.
Which brings us to the ultimate verdict on Kepler 442b. Is it a thriving Earth 2.0 or is it a completely frozen wasteland? Well, because our current telescopes just aren't powerful enough yet to measure its exact orbital eccentricity, we honestly don't know which of these three states it's in. It is currently existing in this thrilling, almost sci-fi state of quantum habitability. It could be a lush, cool Earth twin, or it could be a completely dead, irreversible ice ball. We literally just have to wait for better telescope data to know for sure.
As the researchers perfectly summed it up in their paper, the climate of a planet is certainly affected by its spin-orbit condition. Habitability is defined by the possible stable presence of liquid water. And I think this brings us right back to the core lesson of this entire explainer. Finding a planet at the right distance from its star, that is literally just the beginning of the story. The complex gravitational dance that dictates a planet's spin, combined with the exact type of radiation coming from its host star, those are the things that truly dictate whether a world can survive as a cradle for life.
And this brilliantly illustrates the exact, staggeringly rare recipe we need to finally crack this case.
It's not just about finding a rock the right size at the right distance. The true Earth 2.0 likely demands a K-dwarf star for stable, gentle radiation. It needs an orbit securely in the habitable zone, and crucially, it needs an initial planetary spin and eccentricity that protects it from the terrifying deep freeze of tidal locking. It is an unbelievably delicate cosmic balancing act.
But you know what? While those conditions are remarkably strict, the galaxy is unimaginably vast. Somewhere out there, an alien world is likely spinning perfectly in the Goldilocks zone of a bright orange sun, maintaining a fast rotation and keeping its global oceans nice and warm. The clues are all there, hidden in the data, and our telescopes are only getting more powerful. So will we be the generation to finally crack the case and find it? The search continues. Thank you so much for joining me for this explainer, and as always, keep looking up.